In this problem, what you're looking at is a diagram of a thrust reverser of a turbofan engine. I'm showing you two views. This is a view down the front of the engine. Air is drawn into the fan. And from the side view, we're looking at the fan as well, and air is drawn from right to left through the fan, through the back of the engine. And when an airplane lands, it will close doors on the back side of the engine. Instead of directing the thrust straight backwards to propel the airplane forward, it redirects the thrust, and the air in the engine, it curves backwards in this direction, and it pushes the air towards the front of the airplane, and it slows it down. In this problem, with some parameters that are available to you, we want to calculate how big is this reverse thrust. One thing that we know is that the diameter of the fan is 2 meters. And we know that the engine is drawing in a mass flow rate of air of 500 kilograms per second. The air flows through the engine, and it's deflected by an angle of 60 degrees from the horizontal. Because the air is heated as it flows through the engine and expands, and more importantly, the area on the exhaust is somewhat smaller, the velocity exiting through the thrust reversers, we'll call it V2, is 3 times the magnitude of the velocity entering the engine, which we'll call V1. What's a little bit tough to see from this diagram is not only is the air being deflected in this direction, it's also being deflected at 60 degrees, part of the engine away from you, out of the screen, and part of the engine into the screen. We can visualize that maybe by looking straight at the engine with this diagram on the left. The air is flowing out at you and away from the engine at an angle of 60 degrees. So the geometry is not all that simple. If we look at the side view, it's not simply moving upward and downward at that angle, but rather it's radially a symmetric problem. And that's convenient in this problem because we don't have to worry about thrust developing asymmetrically, or a thrust developing more in the vertical direction of in the y direction or in the z direction into or out of the screen. We only need to worry about thrust being developed in the horizontal or x direction. So let's begin this problem by drawing a control volume, and I'm going to draw it around the thrust reversers. And as I'm drawing it, just for convenience to make our lives easy, I'm drawing the control volume everywhere perpendicular to the flow. So I'm going to draw it straight along that fan, and I'll come back and close it off in that direction. And in 3 dimensions, this control volume, you could imagine it would be, I'm trying to draw it all the way around the engine itself. But in all locations, I'm drawing the control volume so that it is perpendicular to the flow. I brought in the momentum conservation equation in the x direction, and because I only care about the x direction, I haven't included the y and the z directions. One thing that's going on is that this problem is at steady state, and under steady state conditions, this time derivative will go to 0. So what we need to do is brainstorm all of the forces acting on the control volume, and then identify locations where fluid flows into and out of the control volume. Now, the only force acting on the control volume is the force of the thrust reversers on the air. That force will occur on this back region of the engine, and what it does, we've got momentum in the negative x direction entering the engine, and it leaves the engine. It has momentum in both the positive and negative y direction, but more importantly, it now contains momentum in the positive x direction. So it's gained momentum. And what we'll find is that the net force acting on the air, or acting on the control volume, is actually in the positive direction. And that may seem strange because the velocity of the airplane is from left to right. So to slow the airplane down, we would expect that there would be a reverse force acting on the airplane to the left to accelerate it in the negative direction. But what we'll find when we work with this equation is that we'll find a force acting on the air in the positive direction. And by Newton's third law, it means that the air is acting on the thrust reversers in the negative direction. So let's write it out. Let's say the force of the reversers acting on the air. And that force is the only force acting on the air. You note that the sum of forces is not 0 in this case. It's not a static problem. And now let's identify where air crosses the control volume. Of course, it passes through the fan at the entrance and then exits the control volume through the thrust reversers. And I've called these locations 1 and location 2. So let's break this area integral up into 2 separate area integrals. The first one will integrate over the surface area of the fan. So we'll say u rho v dot n dA for the fan. And then surface 2 is the thrust reversers, and we'll integrate the same equation over the area of the reversers. Let's evaluate the dot products at these two surface areas. If we examine the fan again, surface area 1, here's the unit normal, N1, and thus V1, because the arrows are acting in opposite directions, is equal to the negative magnitude of the velocity coming into the engine. And if we examine the second surface area, the unit normal on area 2 is acting in the exact same direction as the velocity, so V2.N2 is equal to the positive magnitude V2. What we also need to find are the x components of the velocity at locations 1 and 2. In this case, the velocity v1 is acting only in the negative x direction. So u1 is equal to negative the magnitude of v1. In area 2, u2, the x component, is acting in the positive v2 direction. But we need a cosine theta in there to account for the fact that only some of the air velocity is acting in the x direction. And we can also say that because v2, the magnitude of the velocity, is 3 times the magnitude of the velocity entering the fan, we can make that substitution right now and say that u2 is equal to 3 times the magnitude of v1 cosine theta. So let's come back to this integral. Because I know the velocity u is uniform over the cross-sectional area of 1, this u can come out of this integral. The density of air, let's say it's constant, it can also come out of the integral. And v dot n are also constant because of that uniform velocity, and they come out of the first integral. And we can say that these, all three of these can come out of the second integral as well. Evaluating integral 1 over the first surface area is u1 rho times, and be careful with the signs now, the negative magnitude of v1 times a1, plus the second integral is u2 rho now times the positive magnitude of v2 times a2. What I can also note is the simplification that the mass flow rate is equal to the density of the air times the magnitude of the velocity coming into the engine times a1. All the mass coming into the engine has got to leave through the thrust reversers, and that's equal to the density of the air times the magnitude of the velocity at v2 times a2. And I'm going to make that substitution on both of these terms, and I'll come up with an expression for the thrust of the reversers acting on the air. What I also know is that u1 is equal to the negative magnitude of the velocity entering the engine, and that's equal to a negative, and I'll use q1 for the volumetric flow rate, divided by the area of that fan. The volumetric flow rate, I can express that as the mass flow rate divided by the density times a1. And I know that u2 is equal to 3 times the magnitude of the velocity entering the fan times the cosine of theta. That then is equal to 3m dot over rho a1 cosine theta. So I'm going to make this substitution for u1 and this substitution for u2, and I'll come up with a simplified expression for the force of the thrust reversers on the air. What I find is that the force of the reversers acting on the air scales with the mass flow rate to the second power. And what's more significant is that it can never be negative. If the thrust reverser is never negative as long as that angle theta is 90 degrees or less. And in that case, if it was 90 degrees, for example, the reversers would just direct the air vertically. So finally, what's important to note, if we use Newton's third law arguments, what we're interested in is the force of the reversers on the airplane, because it's the force of the reversers attached to the airplane that actually slow it down. That'll be exactly equivalent to the force of the air acting on the reversers, and that's equal to the negative of the force of the reversers acting on the air, which is what we found by this analysis. So if I plug in numbers, ultimately the force of the reversers on the airplane equals negative 200,000 newtons. And this is equivalent to negative 45,000 pounds acting in the negative x direction.